normal? Will the customer be happy, or will it be deviant? Is it a fraudster, or is it not a fraudster? Is it going to be late, or is it going to be on time? You take any label, we call it a label. And we have a bunch of traces, and the traces are complex symbolic sequences, meaning sequences of events with an event type, a timestamp, and a bunch of data attributes, each of them. And we try to ask you questions like, will it end up in a negative outcome, will we violate an SLA objective, etc. Unlike deviance mining, and all the other tools I show you, where the user is an analyst, in predictive monitoring, maybe the tricky bit, from a tooling perspective particularly, is that the users are the people who are executing the process. So it's about generating alerts, making recommendations, so it kind of relates to recommender systems, to the process workers, so that they spot the cases where the customer will complain, and they try to prevent it. In predictive process monitoring, as opposed to prescriptive process monitoring, we are only interested in predicting. This is going to go wrong. Up to you what you do. The next step after that, which we have not tackled, is prescriptive process monitoring, which is like, and if you do this, if you give this candy, then it's going to be okay.
Have you considered this prescriptive?
I have considered,
but not
nothing more than considering it. Yeah, but with I see that Kuldar is on for a joint project on that. There you are, because it relates a lot to agent systems.
Yeah. Just a question: business flows. Is this relationship automated? Is it somehow? Does it check against them in an automated fashion?
No, this has to be formalized as a rule. So the business goal is my term to say the labeling function. The function that given a trace will tell you this is a good one or a bad one, or this is of type A, B, or C. From a business perspective, that means a goal. It could be your SL service level objective. It could be your whether the customer will be satisfied or not, your notion of anomaly, etc.
Like metric.
Yeah, it could be derived from a metric, so cycle time, and you can put a threshold, cycle time greater than X, for example. It could be an indicator, actually. No, you are right. I'm also going to talk that we can use it also in a regression mode, which means to predict the remaining execution time. Yes, it can also be a metric, indeed. So it's a fuzzy word to say everything the people who are executing the process in the business would like to predict. The thing they want to predict. So, for example, in a debt recovery process, well, whether you receive the payment or not, that is the business goal. And that's the thing you want to predict. And this is a case study we did with Info Register OU, where we take one of their processes for debt recovery, and there are tasks like events like the debt payment is due, there are tasks like calling the debitor, sending a reminder, receiving the payment, and so on. Each of these events has a bunch of attributes like the customer who we are calling, the person who is handling the case, the history behind it, all the previous payments, and so on, and the amount of the invoice in the first place for which we are trying to recover the debt, and so on. And a bunch of text notes. So the debt collector's right, I think it's completely useless to be calling this guy, for example. Whatever they want to do. Right. Sometimes it does get a little bit longer. Typically, coincidentally, when it gets longer, it ends up in a negative outcome. But when we are here, we actually don't know yet. And that's what we want to know. We want to know with the first 3-4 events, is this going to encashment and we should kind of send it straight to the bailiff, or is it worth pursuing it? The general way of handling this, I mean, it's not new in machine learning, will be like for every trace in the log, you come up with a Fisher vector of a fixed size. For every trace, it kind of has to be of the same size. And preferably no null values, because if you start leaving empty values, your classifier is going to go bananas. And if your goal is a binary or NRE goal, like you want to predict whether the case will be on time or late, or you want to predict whether the customer will be satisfied or not, you throw it into a classification technique. It builds a classifier. At runtime, you give him the Fisher vector of the ongoing case, and it tells you yes or no with a certain confidence. Or if you use it in regression mode, then you do the same thing, give it to a regressor, and it tells you what is the remaining time. Or you can do some predictive monitoring tasks are like of type of structured learning, which means you want to learn, for example, all the possible futures of this case and their probabilities. Or you want to learn the most likely continuation of this case. Or you want to learn to predict the next event only. And the next event and when it will happen and who will do it. And all sorts of combinations. So it's predictive process monitoring is a general class of problems which is essentially about early classification or estimation, regression or prediction based on complex symbolic sequences. By complex symbolic sequences, I mean sequences of tokens, activities in this case. Each of them has a bunch of attribute value pairs and of heterogeneous types, possibly even text. So we have tried a lot of techniques. In this field, what we have done is to try and fail and learn. So we have tried a bunch of techniques. The first one, very simple. I take a prefix of a trace, only looking at the control flow, which means only looking at the token, the event, the activities that have occurred, nothing else. Is a string. I find from the historical traces I have seen, let's say I have seen hundreds of cases before, I find the 50 nearest ones in terms of some distance, like a string edit distance. And I take those 50 and I build at runtime a classifier just with those 50. So I build a decision tree or a random forest. Then I give him the current trace to the random forest, and it tells me, and the random forest is constructed with all the data atoms. And it tells me, yes, this is a good one, or no, this is a bad one. So that was kind of our baseline, and we tested against some real-life logs, including there are some public logs available. There's a website called BPI Challenge. Every year there's a different challenge, and there are logs of hospitals, banks, insurance companies, Volvo, etc., where you can try out your process mining or predictive process monitoring skills on them. So we took some of them and we defined some business goals, like different types of performance objectives we might want to have on this log, and try to make prediction on these 5 logs, phi 1 to phi 2. And we got this accuracy measured by AUC of up to 85%, which is kind of not bad. But it's not good at all, and it is very slow as a technique because you construct your classifier on the fly. For every prefix you want to classify, you construct a new classifier and you use it once and you throw it away to the garbage. Next time you have another case, you will construct it again, compute the KNNs, reconstruct the classifier, use it once and discard. So we said there must be something better than that. So we said but we found the accuracy is quite good. So we used this approach that we call cluster and classify. It's kind of quite used in machine learning as well, which is that we say it looks like it's very good to classify a case by looking at those other previous cases that are similar in terms of control flow to the current one. So then we take the historical logs, all the prefixes of the historical logs, and we cluster them. So we build clusters of similar prefixes. And when I want to, and for each cluster, we then take all the data of those cases and encode them into Fisher vectors and build a classifier to be able to predict for that traces in that cluster. When we have a prefix, we look for the closest cluster. We compare it to each cluster. We found the closest one, the one that has the closest medoid, and we use the classifier that we built for that cluster offline. We use it to classify that case. And the advantage here is that offline I created 40 or 50 classifiers for 50 different clusters. But online, I only need to take a prefix, look for the corresponding cluster, apply the classifier, and that's very quick. So it's very, 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 very runtime efficient. But offline, not very efficient. So we apply these and with different types of encoding techniques, because there are different, one of the tricks of going from sequences to Fisher vectors is how do you encode it? We try different types of encodings. We try different clustering techniques with different parameters. and we tried different classification techniques, and we tested the accuracy. Each of them has certain parameters, and what we found is that on similar experimental environment, we find that the accuracy is probably even better than the runtime approach. It's quite good, but it's very variable. Sometimes it's very low accuracy, sometimes it's much higher accuracy. So it's like if you get lucky, you get a good prediction, because you found a cluster that matches nicely the current prefix and you get a good prediction. But sometimes you get unlucky and you get whatever. So what we did on top of that is that we did something called hyperparameter optimization, which means that for every cluster we compute, which means essentially that we try conceptually all possible encodings, all possible clustering techniques, with all sorts of different parameters and all sorts of decision tree learnings for every cluster, and we try to find the very best tuning, the most tuned, the best tuned classifier for that cluster. So every cluster has a super optimized classifier which is very accurate. And then, not surprisingly, we managed to get this kind of fixed, and the results were much more robust. But what we found is that the execution times were very bad for the offline components. So in some cases, we have to literally train classifiers for like 2 days, 3 days, and this is not going to fly. So we tried other techniques. One technique that I really love, and if you ever get into sequence classification, I kind of recommend to try this one as the first one. You have a sequence, and your problem is a predictive monitoring problem. Some traces are short, some traces are long. And here's a simple trick that turns out it works. You build one classifier for all prefixes of size 1, one for all prefixes of size 2, size 3, size 4, length 4, length 5. So say you want to predict up to length 7, so you build 7 classifiers. Now, how do you get the feature vectors for length n? Let's say n is equal to 5, so the length of 5. You use what I call a lossless encoding. It's like a tuple in this feature vector maps directly to the corresponding trace. I can reconstruct the trace. From the trace I can come here, and from here I can go to a trace, completely isomorphic. You say, you put one attribute for what's the event in the first position, what's the event in the second one, in the third one, up to the 5th position. For every attribute value, like for example the invoice amount, or the customer ID, or the shipping address, you type in, what is its value at point 1, at point 2, at point 3, at point 4, at point 5? Well, if it's an attribute that never changes, then there's no point, but if it changes over time, then you encode its sequence of values. And you do the same for every single attribute. And the same for the timestamp. What was the timestamp at which the first event completed, the second event completed, the third event completed? And it's a pretty long feature vector, but it's fixed length. For an event log of size 5, I'll give you a fixed length vector of size like 100. And I was very afraid. I said, wow, 100 attributes into a machine learning technique is going to drive it nuts, especially that we typically only have a few hundreds or thousands of rows. But what we found is actually that, modern classification techniques are not afraid of long feature vectors. So we use this lossless encoding, which we call index-based classification, and we even dare throwing in some few more features to it, so just in case. So what we do is that we use a generative model called hidden Markov models. We construct a hidden Markov model from it's a stuff that recognizes the language, essentially. It kind of probabilistically generates a language. One for the bad cases, one for the good cases, only out of the control flow. And then when you give me a prefix, I can compute what we call the log likelihood ratio, how likely it is that it's normal or deviant on the basis of this probabilistic model. And we write as additional attributes the log likelihood ratio of being a good trace or a bad trace for every event that has occurred for at every state 1, 2, 3, 4, 5. So you can imagine that if it's telling you, I think it was deviant, was normal at 1, but at 2 I thought it was deviant, then I thought it was normal, but then it was deviant, then you say, oh, this is probably deviant, because that's the trend. The HMM is not changing its mind. And similar experimental setup, and what we find is that this index-based encoding consistently outperforms these other lossy encodings, like where I only keep how many times every event has occurred in the prefix, or whether the event has occurred or not as a Boolean. So lossless encoding, even if you have a big Fisher vector, better than a lossless encoding, which is kind of the trend in machine learning, right? We also, because of these real life scenarios we had, we started dealing with the problem of like, oh, there is text in this, text being recorded in these systems, what do we do with it? So we applied text mining techniques and integrated them into our frameworks, that for every text extracts like a vector of probabilities of distribution of n-grams or terms. And we tested it on these info register logs, and we found that we could predict whether the case will be true, paid or not paid, with up to 75–80% accuracy on this log, which is not bad, particularly compared with some baselines where we do not use the text attributes. And we made some observations about essentially that for these kinds of text that people will write when they are executing a case, in essence, simpler models like bag of words outperform more complex models like latent direct allocation, and they definitely outperform neural network models like paragraph vectors.
What's the balance of those samples like?
Very unbalanced, actually, about 95–5. But obviously, when we trained and tested, we did we balanced it out. Yeah, so it's true. It's a fair accuracy measure. Many deviant predictive monitoring problems, many of them are imbalanced. So you have to make sure that when you train, you rebalance by means of pruning or boosting or duplication. What we are trying now is to move out from this predicting the outcome, is it good or bad, to predicting what is the next event, when will the next event happen, what will be the event after the next one, and after the next one, what is the continuation of the whole case. And there we are using these deep learning techniques, particularly recurrent neural networks with long short-term memory architectures, and they can predict, we have tested different architectures for predicting what is the next activity, when will the next activity happen. We found out that predicting the two at the same time, building a single LSTM that predicts the two at the same time rather than two LSTMs that predict each one separately, is actually better. And we have also started testing stuff like predicting all the sequence of next activities up to the end. And then we have compared against existing baselines that are based more on this style of feature vectors. I construct a feature vector with meaningful features and I give it to a classifier. Here we just encode the data losslessly, a bit like I showed before, and we construct these deep neural networks with many layers to turn those into intermediate features, and then into a final prediction. And this is kind of ongoing, but it seems like we are able to beat a lot of baselines. And what is interesting is that with the same LSTM model, we can beat a baseline that does predicting the next event, another baseline that predicts the continuation, and another baseline that predicts the remaining time of a case by doing regression. So that's basically what we have. I didn't intend that you kind of catch everything. I'll make the slides available, and in the slides I have the pointers to all the codes of all the techniques for predictive monitoring that I have mentioned. There is code in Python or in R, whatever you prefer. We also have it in Java because we have integrated into a tool called PROM, an open source process mining framework, which is entirely written in Java. And that's all I wanted to do today. If you have any questions. Yes?
So this the lossless encoding provides good precision or productivity.
Yeah.
But can you characterize somehow the scalability? What are the practical bounds?
Sorry, I forgot to say that this multi-classifier approach where you build one classifier per prefix is very scalable if the length of the traces you are looking for is small, because the complexity depends on how many classifiers you have to build. When we did cluster and classify, we had to build like 50, 60, 70 clusters, 50, 60, 70 classifiers. Each of them had to be hyperparameter optimized, which is a very time-consuming process. With this one, it depends for how long you want to make the prediction and how long your traces are. If your traces are like on average 30, 40 events, which is a typical business process, relatively simple business process, then you might just want to predict up to 1/4 of the case, which is just the first 10, and you just need 10 classifiers. So it is in the number of classifiers. Now, we did work a bit with Telia, looking at some processes where there were work orders and there were lots of events on the work order. And we found that two things, that of course the number of events was quite long, so we had to build a lot of classifiers, but also that sometimes cases advance very quick and other ones very slow. So a trace can have 10 events, but it's in a very advanced state. So you cannot classify it using the classifier for prefix of less 10, because it turns out this one is abnormally fast. And then you are using the wrong historical samples to classify it. So what we did with them is that we said we're going to use the same, but instead of doing one classifier per prefix, per like size 1, length 1, 2, 3, 4, 5, we do it per milestone. And a milestone, you can define it whatever way you want. In their case, it was like every time when the first work order finishes, when the second work order finishes, when the third work order finishes. But it could be every month. Once a month we do a milestone. And then you have much less classifiers because you just do one per milestone. I think we're being kicked out, right?
Yeah, I'm very sorry. I didn't want to do that, but apparently the clock on the wall is wrong. It's a bit behind. And I ask you to perhaps join in the coffee room so we can answer a few more questions in there. We will be on the 4th floor to grab a coffee and have a chat on these topics if you're interested.
Cool.
And thank you very much for the invitation.